Thanks. So thanks, Vignesh, for the nice introduction, and a very good afternoon to all of you. Uh, so yeah, so as Vignesh was telling, like it's about midnight here in India. So hopefully I'll be able to continue the talk. So anyway, so let me just talk a bit about this set of research that we are doing at IIT Kharagpur. So this is basically a very interesting problem in the domain of pervasive and ubiquitous computing. And typically, if you look into that in several pervasive and ubiquitous computing problem, what we broadly do that we collect the data through certain sensors, annotate the data, and try to develop certain model to predict something about the environment or the context or so on. Right. So broadly, what we are going to talk about is like this context of multimodal sensing, where you have multiple different sensors that are deployed in different spaces, and nowadays we keep on talking about different type of smart environments, smart cities, and so on, where you have multitude of such sensors which are continuously collecting the data, and then you basically need to annotate the data, and through the data you try to understand the context. That might be the environment, that might be the human behavior, human gesture, and so on. Now, the interesting fact here is that if you look into the most of the research in this domain, they typically assume that, well, the data is being collected through some sensors, and then there would be human annotators who are going to annotate the data, and that way you get the annotated data, and finally you use the annotated data for building up your learning models. Now, one problem that we typically ignore is about this annotation of the data. So what we think of in general that whenever the data is being annotated by some human, that becomes the kind of gold standard, and you can use that annotated data to build up your model. So we started thinking of, indeed, that came from our experience in working on this area of pervasive sensing while doing the annotation. We found that, well, this kind of annotation has several problems, several kind of challenges. But one interesting problem that come up is that uh, how can we effectively label all these kind of multimodal data? Well, and as I was saying, like we use different type of platforms like this Amazon Mechanical Turk, Yandex, Crowdflower, Sama, and all these different platforms are different type of problems, like they are time consuming, they are expensive, you need to do the crowdsourcing, and whenever you are relying on crowdsourcing, the question comes about the reliability of annotation and so on, right? So for example, if you look into, like if you think about the Amazon Mechanical Turk, if you try to annotate some 1,000 image with two different levels of the image, so typically that could take around 4 hours or even more than that. Well, and if you look into the price, with that 1,000 image of two levels, it can cost of some $300 of US dollar. So that way they are expensive as well as time consuming. But even apart from that, the major problem that comes up is about the reliability of the data or the reliability of the annotation. So we started looking into this reliability of annotation, and one interesting fact that we observed is that, and one important thing is that the data annotation is not only for this kind of pervasive computing or pervasive sensing kind of problem, but this data annotation is also a problem for any kind of machine learning task, and there have been a lot of work for this automated data annotation process. So for example, if you are trying to perform an NLP task, a natural language processing task, you need to do data annotation. If you want to perform certain kind of image processing task or video processing task, you need to do data annotation and so on. So data annotation you need everywhere where you are going to apply certain kind of supervised learning algorithm. But if you look into the nature of data annotation, here comes a very interesting observation. Say, If you look into the other domains, like the domain like computer vision or natural language processing, there, so for example, in case of computer vision, you have a video which is being given. By looking into that video, you need to annotate the data, and that annotation can be of multiple different types. So for example, if you are trying to annotate the activities that are being performed, like say a horse is running, so you are annotating the video data, or rather the video, and the same video file is being used for training your model, right? Similarly, if you look into the natural language processing, where say for example, you have certain text which is being given, and you need to label that text, might be again the activity labeling, or even there are different kind of labeling, like you want to label so there are lots of work on hate speech detection. You want to label a particular text as a hate speech. So you label the text. So the text that you are being labeling, the same text is being used for your model training purpose. But interestingly, if you look into the pervasive sensing community, so what you are going to do, you are going to collect the sensing data from the environment. So for example, you are going to collect the accelerometer data, maybe from the horse. But while doing the labeling, you are not actually looking into the accelerometer data. Rather, what you are doing, you are looking into a third modality, maybe the video of the horse running, well, and from there you are labeling the data. So that means the data labeling is being performed on one particular modality, maybe the video, well, or there might be third person who are observing the person to do the work and labeling the data, whereas the model is being trained with the data from a different modality, say the accelerometer or any kind of wearable sensors that are being mounted, or any kind of other sensors that are monitored on the environment. So that means the modality, the sensing modality, which is being used for labeling, and the sensing modality, which is being used for annotating the data, they are different. And that brings up several interesting problems. Well, so throughout this talk, I will try to highlight at least 2-3 such different problems that we have observed, and the way we are trying to tackle those problems during data annotation. Well, so let me see that how much I can cover. Okay, so the first problem that we started thinking of that, well, in this pervasive sensing domain, can I develop a method for automated annotation of the sensing data? Well, and a particular use case of the application that we have thought of that, well, this gesture recognition or the human activity recognition. So when you are having certain kind of wearable through which you are collecting the activity data or the gesture data, and then you are trying to label that sensors, the kind of wearable sensors, it might be accelerometer, gyroscope, or that kind of sensor, and then you are applying that for human activity recognition. Right? So the broad question that we are going to ask that how we can do an automated annotation of the sensor string. Well, so what we have observed by looking into the prior modality, prior work, that there have been some works which particularly have taken video as an auxiliary modality. So you take the video, and from the video you try to automatically identify the activity on the video data, and then use that data to label your accelerometer sensor or the wearable sensor, right? But video has different kind of issues, like it is privacy sensitive, it is computationally expensive. So for example, in one of our problems, we need to collect this wearable data from the older people. The objective was to monitor their daily activities to find out whether they are having ongoing symptoms of dementia or cognitive impairment or not. And in that case, we need to have a wearable device called a Empatica E4 device, which have been owned by those old people. And we are monitoring their daily activities from the accelerometer data and many other sensors that were there within that Empatica. But the thing is that for the ground truth labeling, obviously I cannot put up a camera in the house of those persons and start collecting the ground truth data. So that is kind of not possible. So what we thought of that, whether we can use any kind of alternate modality for do that, right? And one thing that came to our mind is about the acoustic signal. Now the acoustic signal, from the privacy perspective, you can still say that, well, the acoustic signal is privacy sensitive as well. But one of the advantages that we have with acoustic signal is that the processing of acoustic signal is much more lightweight compared to processing of the video signals or the video data. So that way, what we can possibly do, we can try to build up lightweight models or lightweight approaches that we can run on the edge devices that are deployed on the home itself. So what it can happen that it can basically observe the acoustic signal. From the acoustic signal, it can find out the activity classes and can accordingly label the data. And it can do it on the device itself so that I do not need to take the acoustic data outside my home. That means it remains within the periphery of the home, and that way we can try to preserve the privacy out of it. Well, so but there are still several challenges if we try to use acoustic data for annotating the activities. Well, so the broad idea was something like this. The core idea that we have applied, that say a person is performing certain activity, and the activity is going to generate some signature, some acoustic signature. So the person is having certain wearable, say a smartwatch, which is collecting the wearable sensor data. And in the environment, I have a microphone, which is capturing the acoustic signal. Well, and then what we need to do, we need a kind of synchronization between these two modalities. So remember that here I do not have any kind of label a priori, so I cannot use any kind of supervised model as such. So I need to go for an unsupervised approach. And in an unsupervised approach, I need to understand that what are the activities that is being performed and how that activity is getting synced with the sensing modality that we are capturing from the wearable device. Now for that, what we do that from the IMU data or the accelerometer data that we are capturing from the wearable, we detect the change points of those physical activity. Well, we check the corresponding acoustic signature, and then from the acoustic signature, we detect the activity. So in the acoustic signal processing domains, there are multiple different models, and there are even publicly available large models which can infer the human activities quite accurately from the acoustic data. So you use those existing pre-trained model and infer the activity information. Well, and then you label the IMU data with the detected activity level. Well, so that's the kind of broad idea which we applied. Well, and the advantage, as I was mentioning, is that you can precisely detect the activities from the acoustic data. Although the kind of assumption is that the type of activities that we are trying to detect, they generate sound. Obviously, if your activity doesn't generate any kind of sound, you cannot label it any further. Given that this acoustic signal processing is much more lightweight, you can execute them over the edge device itself. You do not need to take the data out of the data territory. So that way the privacy gets preserved. And the big advantage that we have is that you have existing rich data set of human activity labeling for the acoustic data, like you have this YouTube 8M data set, which has the acoustic signal from different type of activities. So you have those kind of pre-trained model that you can use effectively to detect the activity labels from the acoustic signature. Well, so that was the kind of our broad idea. So we named it that model as Lasso, which got published in ICMI in 2021. So I'm not going to the details about the model. So the broad idea was basically to detect the change points, and once we detect the change point, then based on the change point in the IMU signature as well as in the acoustic signature, you make a match between the IMU data and the acoustic data, and accordingly transfer the label from the acoustic signal to the IMU signal, right? And what we have observed that for different kind of environment, we got quite a good accuracy in doing this automated annotation. So for example, in a workshop environment where most of the activities generate precise sound, we have around 98% of accuracy, whereas, 93% of accuracy, whereas in a kitchen environment where some of the activities generate the sound, but some doesn't, in those cases we have close to 80% accuracy. Well, so that was the kind of broad idea. But the thing is that this method looks simple, but it gets complicated when you have multiple different persons in the same environment and they are performing the activity simultaneously. So for example, two different persons are doing the activity simultaneously. Well, now if two different persons are doing the activity simultaneously, then the acoustic signal that you are actually getting, that is a kind of convoluted form of the acoustic signal where the acoustic data is getting generated from both the activities simultaneously. So that means you are here not getting a single acoustic signal to get the activity level, rather you are getting a convoluted acoustic signal. So the question comes that with the help of that convoluted acoustic signal, how can you generate the activity levels? Well, and this actually triggers a very interesting problem. If you try to use the acoustic signal to do the activity annotation. Now the thing is that as a measured signal, what you are getting at the end is the convoluted acoustic signal. You do not know that which person is doing the activity, that what kind of signals are getting generated. Well, so just think about this scenario that you are outside the door and you are getting two different sounds, right? Now the question is that there are two different persons who are doing different activities. So that is a kitchen environment. One person is doing cooking, another person is just chopping the vegetable, and you are getting a combined sound. Well, so the question is that how you are going to do the mapping of that sound signal to the corresponding activities. That means how are you going to understand that who is doing cooking and who is chopping vegetable? Well, and because you do not have any kind of signal apart from the convoluted acoustic signal that you have received and the corresponding IMU data that have been captured from the wearable sensors of the individuals. Well, so here is the kind of interesting idea that we observe by analyzing a huge volume of data. So what we observe that unlike the mechanical sound is in the sense like the sound that is being produced by the air condition or any kind of motorized device, which basically generates continuous sound. The sound which is generated from the human activities, they are discrete in nature. That means they doesn't generate continuous sound. Say if you look into the sound pattern of chopping, you will see that you will get a sound like when the knife hit the board, a sound is generated, then there is a gap. Then again, a sound is getting generated and there is a gap. So that means between the sound signals, you have a period, a silent period that naturally comes for the sound which is being generated from the human activities. And that gap, that silent gap, we call them as the acoustic gap. And we take help of this acoustic gap to actually identify the corresponding activity signature. Well, and as I was telling that this kind of acoustic gaps are very common in general human activities. Well, so there are different reasons that people take this kind of acoustic gap, like to reduce the extortion, to increase productivity, and so on. Well, and these acoustic gaps can also be there due to micro activities. So, for example, the person is chopping the vegetable, and in between, he or she is cleaning the knife. Okay, and while cleaning the knife, means as you can show in this animation snippet, that whenever there is a cleaning of knife, then you get that acoustic gap, the silent zone for that particular person. Well, and that way in any kind of human activity, if you observe closely, we'll see that there are this kind of periodic acoustic gap which comes naturally. Well, so what we do that we take help of this acoustic gap to develop this framework of automated data annotation, which we call as annotated. Well, and the environment setup is similar to earlier. Only difference is that now there are multiple different users who are performing multiple different activities. Well, and all of those users, they are having some kind of smart wearables with them, particularly a smartwatch or other kind of sensors, which give me the IMU data. And my objective is to get the convoluted acoustic signal. And from that convoluted acoustic signal to match or to find out the activity level, and then accordingly label the individual activities corresponds to the IMU signature that we are getting from different variables. So here is the core idea. So what we do that, again, we look into the change points. Well, but this time what we do that we look into the change points of all those different IMU signals that we are getting from different persons. Well, and also look into the change point in the acoustic signal. Now, if you look into this diagram, what you can see that for one person, the top person, so that is the IMU data from say person M, and the bottom one is the IMU data for person N, and the middle one is the data from the acoustic. Now you see that there is a period of acoustic gap when your acoustic signal is very low, that means it is in the silent zone. Well, and within that silent zone of one person, basically, for one person, again, you have kind of more of a kind of static value in the IMU data. Whereas for the other person, there is these changes in the IMU signature. Now, by looking into this, what you can possibly infer that for the person N is performing certain activity during that period of time, and within that period of time, person M has a silent zone, that means the acoustic gap. That means the acoustic signal which is being captured during that gap period, that corresponds to IN. Okay, so that way we basically find out the opportunities of acoustic gap, and from that acoustic gap we infer the activity level, and in the IMU signature find out that for which particular person that signature is prominent, and accordingly do the mapping. Okay, and that way we develop this entire end-to-end pipeline, and this entire end-to-end pipeline has 3 different steps. So in the first steps, what we do that we take the data from all the sensor units, and the data from individual sensor units, they are processed independently, and then we detect the change points in the IMU through change point detection algorithm. Particularly, we use something called Ralsif change point detection. And after finding out the change point, we apply a clustering method to actually cluster those change points to find out the similar type of change points. Well, and in the acoustic signature, what we do that we apply signal processing techniques on the acoustic signal. Basically, we apply this cross power spectral density, capture the cross power spectral density from the acoustic signal, which actually provides a robust solution to detect the acoustic gap. That means it can tell me that, well, in the convoluted acoustic signal, so if that signal is getting convoluted from 2 different sound source, then at this particular time zone, only the sound from a single source is present. That means for the second sound source, there is acoustic gap at that point of time. Well, basically, what happens that the value of the this cross power spectral density get at a lower flat, kind of lower flat at that point of time. Okay, and basically, if you have a higher CPST value, that depict that has similarity between the two audio sample. Now, once we pre-process this acoustic data and the audio data, we get the change point from the acoustic data, and we identify the that acoustic gap from the audio signal. Then our model searches for the user who entered in the acoustic gap. Okay, and that way we apply something called exclusive change, and the idea is that in the global audio, if we see that there is a change in the IMU signature as well as there is a change in the audio signature, well, that basically means that the IMU signature that gets changed for one user, and because of which it reflects in the audio data, and we observe a similar change point in the audio. Well, so that way we detect the exclusive change which marks the user who has entered the gap. So that means for a user, say for example, there are 2 users, myself and someone else. Well, for me, an change in the IMU signal is detected, whereas for the second person, there is no change in the IMU signal. But at the same time, I see that there is a change in the acoustic signal. That basically means the change in the acoustic signal is due to the change in the IMU signal in my data. Well, and that means I have entered an acoustic gap. Okay. Then at that point of time, our model queries the audio-based activity recognition module to detect the corresponding activity level of the user. Well, and in case there is a conflict, then this annotate relies on the user who has entered the gap more number of times. Okay, so basically it tries to find out the opportunistic users across multiple different users. Well, and finally, to do the annotation, what we do that one important challenge that comes up is that the changes that we observe in the IMU data and the audio data, they might not be perfectly synchronized, okay, because they might get captured at a different point of time. You remember that whenever, say for example, I'm doing a chopping and then I'm taking a break from there, that particular things might get reflected in my IMU signal immediately, but the sound, in the sound signal, it might take some time to get reflected, okay, because the device is somewhere else. It might happen that at one instance of time the sound got generated, then it doesn't get generated, or the signal of the sound of loads. There can be multiple such different reasons because of which such kind of synchronization problem might come. Well, so what we do that we basically apply an explicit synchronization technique by observing the time series data, and from the time series data by correlating the time series values between the two signals. So we basically explicitly synchronize them and then detect the individual activities out of it. Okay, so that's the kind of broad idea which we apply. This is our basically general setup, that we have multiple different users who are performing the activities, and we get the convoluted audio. And we actually created a data set ourselves, as well as we have used some publicly available data set to evaluate this particular model. And in our model, we have this IMU data as well as the audio data. And for ground truth annotation, just to see that how our model works. Okay, so remember that the model that we have developed is entirely based on change point detection and clustering, and then applying some heuristic to sync them together. So it doesn't need any kind of supervised data as such, but just to evaluate the model, we have used video data, basically timestamp video, which works as a ground truth data. So what we observe about the performance of annotate is that if I see that how good it can associate the activity to the user. So we have collected the data from two different environments, in a workshop environment as well as in a kitchen environment. So in the workshop environment, we found that out of the 12 different instances, in 10 different instances, it could correctly identify the users. For kitchen, it was 3 out of 5. For annotation accuracy, in workshop environment, it was 82%, whereas in kitchen environment, it was 98%. And this is something very interesting, because if you remember, when we did that single user activity annotation during that point of time, the result was otherwise. In workshop, we got a better accuracy, whereas in case of kitchen, we got a lower accuracy, right? Here, it is the reverse thing. That is particularly because when we are doing this multi-user activity annotation, during that time, we are relying on acoustic gap. And as I have pointed out earlier, that this acoustic gap are features of human activities. So the humans are doing the activities. But if you look into a workshop environment, there are multiple different machines, although the machines are being operated by the human. Well, but because of that nature of the machine generated sound, there were less scope of getting those acoustic gaps. So that's why what we see that for multi-user annotation, for workshop environment, we get less accuracy, but for kitchen environment, we get more accuracy. Okay, and this is the kind of volume of data we could annotate with this kind of method. Well, so for workshop environment, we could correctly annotate around 32% of the data, whereas for the kitchen environment, it is 10% of the data. But although the number might look a little bit lower, but you remember that this is something which we are doing completely in a completely unsupervised way. And in the sense, like once you have a part of the data that are being labeled, then actually you can take help of that label data to apply other method like active learning or transfer learning to label the remaining part of your data. Well, so that way this provides a nice way of bootstrapping the automated labeling process. I'll just skip the remaining results, which actually shows the impact of this activity annotation under different environment. Rather, I will just directly jump to the third thing that I was intended to talk about, which is indeed an open problem. We are currently working on it. We got some initial observations, but what we believe is that there are a lot of scope to work further on this area. So the idea is that, as I have mentioned at the beginning of this talk, that this time and cost is one aspect for which we can go for this automated annotation process through a secondary modality. But another important thing comes is that whenever we are going with the human annotation, then whether we can take that human annotation as a gold standard, or whether there can be certain kind of shortcomings in the human annotation that we can take help of machines to sort it out. Well, one interesting thing that we observed is that, well, we can develop different kind of automated data annotation method, but all those methods have certain kind of limitations. So for example, the method that I have just explained that depends on the acoustic signal, and as well as it detects on the accuracy of the acoustic signal processing and so on. And that's the reason that many of the times we need to rely on the human annotator. So we tried to see that how reliably we can use human annotator, or at least we can develop certain method or certain way to assist the human annotator to do the correct annotation. Okay, so we that way tried to analyze the human annotation further and tried to see that what interesting things we can observe on the annotation data by human annotator. So what we did, that the question that we asked, that the annotation that are being done by human, whether they are truly gold standard. Okay, and by looking into the type of problems that can come from human annotation, we have seen that there are three different broad problems that can come up. One is, many of the time the data is unreliable, because you really do not know that whether the human annotator is actually looking into the modality through which it is supposed to do the annotation, or just randomly putting up some values. Well, the second is that sometimes the annotator might get biased. Well, and that bias might not be an intentional bias, that can be unintentional bias or a perceived bias towards certain environment or towards certain activities. And the third thing is that is erroneous labeling. Okay, so that might come because of the inherent confusion of the person. So for example, if a person is walking quickly, okay, and you got the data, so what you are going to label it? So some person might think that, well, the person is running. Some other may think, no, it is not running, it is walking. Well, so some can label it as walking, whereas someone else can label it as running. And this kind of error may come while doing the labeling on the data. But another interesting problems that comes up, particularly for the labeling of such kind of pervasive computing data or ubiquitous computing data, it is the unexplainable labels. Okay, so let me explain that what is this unexplainable labels. So for example, so here are two of the activities. Well, so the first one, you can see that the person is spraying something on a pan. Okay, so what can be the possible label of it? So we actually looked into one popular data set, and both the video snippet have been taken from that data set, which is called the CMU MMAC data set. So whether this spray pan is explainable. Okay, that means whether that is a correct label, or do you think that that might be something else? Similarly, for the second activity, you see that the person is doing something, basically mixing that egg yolk with the batter. and actually both the activities were to bake a cake. The video has been taken from that activity. So for the second one, there have been a linguistic impact. So for example, someone can label it as mixing, someone can labeling it as steering. Okay, so which one is a better label? Well, so that way, what we can see that there can be subjectivity which can come with that human annotation. Well, and as I was telling you earlier, like this annotation in the pervasive domain has this challenge, has this specific and particular challenge, which is possibly not there in other domain like image recognition or natural language processing, because the same data which is being labeled, that data itself is being used to develop the model or train the model. But whereas in the pervasive domain, you annotate the data possibly by looking into that video, whereas you try to train IMU data with the help of that label. Okay. Now that's why the labels need to be much more precise compared to what we see for the other domains. Well, so these are the fundamental queries that we had. Well, that say if I have a predefined label space which has been given to the users, whether such a predefined label space properly corresponds to the range of activity signatures which are being captured through physical sensing. This is very important, and many of the times while we label the data, we do not keep it in mind. We just define some labels depending on what we actually try to do from the data. Well, but we do not think about that whether that entire data set that I am capturing corresponds to this set of labels or there can be something else. Well, and that actually can create problem in my data set, in my training model, particularly because we are training the IMU data. As an example, we are training the IMU data, but we are labeling using a video data. So it might happen that the annotator observes something in the video data and label it accordingly, whereas that is not there in your IMU data, and the model gets learned something else. Well, so this kind of problem might come. So that is the first query that we had, and the second query is that do the activity labels defined within a label space have clearly separable boundaries that are also transparent to the external annotator? This is also very important. Well, say if you go back to the earlier example that I was showing you, in this case, say for the second case, if you have mix as well as star in your label space, just think of that what the annotator can do. So some annotator can label it as mix, some annotator can label it as star. Well, whereas if you look into the IMU signature and try to model this, develop an activity recognition model from the IMU signature, the IMU signature is similar for both the cases. Okay, so this kind of inconsistencies may come while designing the label space itself. Well, and many of the time we ignore this, and there are many practical instances where we have observed that such kind of things are there. Well, so we actually looked into different type of data set and tried to see whether such kind of inconsistencies are there in the data set or not. So we looked into this Grenoble HIS data set as well as something called CMU MMAC data set that I was mentioning earlier. And there have been lot of research works that have been done, that have been published with the help of those data sets. And those data sets are publicly available with the corresponding labels. But while analyzing those data sets, we have found out that there are such kind of inconsistencies which are available within the annotation itself. Well, that means the existing models which are there, they have those inherent problem in the annotation. Well, so we looked into this problem into further details. I'm not going to explaining this graph because of the timing constraint that we have. But what we broadly observed that there is an annotation bias that always come while developing the label space. Because whenever I have certain problem that I try to solve and for which I'm collecting the data using my sensing modality, and at the same time I am having or I am preparing a label space, we do not actually look into that whether for an annotator, the annotator can correctly do the labeling or not. Well, we just define the label space for the objective of our problem. And because of which it brings up different kind of inconsistencies in the label space itself. And that way it affects the model that we have developed with the help of those kind of biased annotation. Well, and this kind of problem persists. Well, so the motivation of this work was that can the physical sensing data itself depict the annotation explainability for a human activity recognition task? That means, can I develop certain kind of automated model which can tell me that whether the annotations are explainable or not? Well, and how do we define explainability? This is a kind of formal definition of the explainability that we have used. Let's say A be an activity annotation for a duration of t to t plus delta, and I be an input physical sensing modality captured for the same duration. Now we demarcate the label A for the duration t to t plus deltas as unexplainable if and only if there is at least one significant change I that has not been accounted for in the annotated label A. That means whenever you are looking into the physical sensing data, what can be the case that in your physical sensing data, if it corresponds to a single label, that entire data should show the similar kind of pattern. But if we say that there is a significant changes in the pattern, but the entire thing is being labeled by a single label space, that means there is certain kind of explainability problem. Okay, and then I will just skip this part in the interest of time because I see that I have around 5 minutes left. We actually did a lot of human survey to understand that what is meant by explainability and whether such kind of explainability persist in the existing label data set. And interestingly, what we observed that they do not. And there are different kind of subjective opinion across different kind of activity labels. And finally, actually, we have came up with a zero-shot architecture with the help of these verb attribute labels to have an architecture where given a data set and given a label space, you can tell whether they are explainable or not. Well, in the sense that whether we can see certain problem of explainability in the observed data set or not. Well, and I'll just show you one example that how it works. So what we have seen that these are the two labels that was there in the label space. Say this scrape big bowl into baking pan. This was one label in the label space, and the second label was pour big bowl into baking pan. Okay, and if I look into the individual micro activities which were there based on those change points, you see there are multiple different micro activities. Well, and if we look into the video, those micro activities can have its own level. Well, so that means that the entire large activity that we are talking about, if I try to label that entire large activity with a single label, that might not be explainable all the time, and that might impact your model. Okay, and with this line also, as I have said that this is an ongoing work and we are still exploring. So these are the kind of trade-off that we have observed in terms of granularity versus explainability, that it is not always true that a very detailed annotation will be explainable, and the added information could introduce unnecessary ambiguity. So many of the time, if you put more information, that will introduce ambiguity in your result. So the open question is how to certify that a given annotation is indeed gold standard. Well, and from that perspective, we thought of, can I bring machine into the loop? Well, within the human into the loop approach. And very recently, we have started looking into that because we have this ChatGPT and this large language model. So can that help? Can my large language model help in doing that annotation? So what we did a very simple experiment to see that if I give my sensing data to a language model, to ChatGPT, what response do we get? Well, so here are two examples. One is from GPT 3.5 and the second one is from GPT 4. The actual activity annotation was running, but we see that, well, in GPT 3.5, many of the time it was talking running, but there are instances when it itself was confused and it was talking about walking, the same instance. And GPT-4 is much more confused because it sometimes says running, sometimes says walking, and sometimes it gives some large kind of answer, something like this. So this large response that you can see here, it is a response from GPT-4 that the provided accelerometer data does not exactly match the typical pattern for either walking or running as described. Okay, so the model itself gets confused. So the language model itself gets confused. Well, so we are thinking of, so as I said, that this is an ongoing work, that we are thinking of that, can I provide certain kind of contextual information to the language model to actually infer the corresponding annotation, which can at least tell me whether the annotation is explainable and whether the label space that are being used for annotation is unbiased. So with that, I will just stop. As I said, that this is an open problem and ongoing problem, and I think that there can be many interesting avenue that can come up with this kind of intelligent annotation problem, and at least to say whether an annotation is correct or not, because all the supervised model actually depends on such kind of annotation. So that's all from my side. Thank you for attending. I'll be happy to take up questions.
All right. All right. Thank you, Sandip. Any questions? All right, Sandip, I have a couple of questions in your first project that you discussed.
Right.
Is there any, so how dependent is the sensing on the location of your microphone? If there are
Good
multiple people doing activities simultaneously?
Right. They are indeed dependent in the sense, so as I have said, that there is always a kind of synchronization problem. Synchronization problem in the sense, whenever I have a single microphone, one user is close to the microphone, the second user is far away. Now, the convoluted signal that I get is actually the delayed signal from the second person. Well, because the person is far away. So what we actually did to eliminate such kind of synchronization issue, that we looked into the time series data, because the position of the microphone is fixed. We looked into the time series data. From the time series data, we tried to capture that lag. And actually, if you do a cross correlation between two different signals, you can find out. So whenever the signal is having a kind of highest correlation, you can capture the lag, that in what lag you are getting this highest correlation. And from that lag factor, we have estimated this synchronization delay and use that delay explicitly to synchronize the two signals while doing further processing for change point detection and then applying the loop.
I see. I see. All right. The next question that I have is, oh, you have, yeah, go ahead.
So I saw in the evaluation, there are two environments. One is the workshop environment, the other is the kitchen environment. My question is, I wonder how they choose these two particular environment. Is there any reason? And are there any other environments that can be used to evaluate the proposed work?
So Sandip, was the question audible?
Can you please tell me the last part of the question? Yeah, I heard the first part, that about workshop and the kitchen, and then what was the exact question here?
To paraphrase, basically the two environments you considered were kitchen environment and workshop environment. Is there any specific reason for picking these two environments, and what are the challenges if we want to do this evaluation to different setups other than these two environments?
Right. So as I mentioned, that because we are relying this acoustic signal as the auxiliary modality, so we can apply such kind of method where where the activities are going to generate sound. So the specific reason for choosing a workshop and a kitchen is that if you look into the activities in workshop like this hammering, sawing, similarly in the kitchen, chopping, cooking or stirring, they generate the sounds. Well, so that's why you have taken up these two environments. It can be applied to other environment as well, but as I have said that the limitation is that you need an environment that where the activities is going to generate sound. So if the activity doesn't generate any kind of sound, our method cannot help. Right. So we have indeed deployed it in many other factors. So in between, I was talking about working on this detecting dementia or cognitive impairment based on activity of daily living. There actually we have deployed this environment in some nursing homes where there are old people who do their work, their daily work over time. So in that case, for the activities which are going to generate the sound, we can annotate that. But for the activities like whenever they are changing their clothes, okay, or whenever they are eating, so those kind of activities are not generating any kind of precise sound. So the method fails there. So the applicability is depending on how much sound or how much noise the corresponding activity is generating.
I see. Okay. Does that answer? Any other questions? Okay, so I was going to ask you in the first case, so what is the maximum number of simultaneous number of individuals you have been able to detect their activity based on these?
Okay, so I have just skipped the graph. So we have tried with 8 users. So what we have seen that with 2 users, it works very good. Even with 3 and 4 users, the accuracy was quite high. It was close to 80%. But as it goes beyond 4 users, we see a kind of sharp drop in the activity because ultimately the model is kind of dependent on how many acoustic gap you can detect. Now, as the number of users increase and they start doing the activity simultaneously, those opportunities of getting the acoustic gaps get reduced. So that's why beyond 4, well, it is not like that the model performed very bad. It's still been able to label some amount of data, but it was comparatively very low